Hello everyone. Welcome to EulSeoggy's Vehicle Dynamics. We will now begin the 6th video on pitch geometry. In this video, we will examine the zero lift and zero pitch angle conditions for front-wheel drive vehicles with independent front suspension. We will also explain the pitch angle based on the positions of 7 front virtual reaction points. The squat and lift of all-wheel drive vehicles, as well as the dive and rise of inboard brakes, will be explained in the next video. If you found this video helpful, please hit the thumbs up and catch the brand new videos by free subscription. Also turn on alarms to be the first to enjoy new videos. Let me introduce the content of this video. In the previous 4 videos, we examined the pitch motion of vehicles driven by solid axles and those equipped with outboard brakes. Additionally, in a recent video, we looked at the pitch motion of a front-wheel drive vehicle with independent suspension. This time, we will examine how the pitch motion differs in a front-wheel drive vehicle with independent suspension. First, we will compare the pitch geometry of front solid axles to that of a front-wheel drive vehicle with independent suspension. Then, we will examine the transmission paths of spring and link forces in a front-wheel drive vehicle with independent suspension and calculate the conditions for zero lift and zero pitch angle using moment about the virtual reaction point. Finally, we will explain the 7 pitch angles based on the location of the virtual reaction point. I have a quiz for you. Which of the following correctly describes the relationship between the position of the front virtual reaction point and the ride height in a front-wheel drive vehicle with independent suspension? 1. There is no relationship between the position of the virtual reaction point and the ride height. 2. As the position of the virtual reaction point increases, the front ride height increases. 3. As the position of the virtual reaction point increases, the rear ride height increases. 4. As the position of the virtual reaction point increases, the front ride height decreases. 5. As the position of the virtual reaction point decreases, the rear ride height decreases. Please select the correct answer from these 5 statements. This time, we will compare the pitch geometry of a front-wheel drive vehicle with independent suspension to that of a front-wheel drive vehicle equipped with a solid axle, which was explained in the previous video, E0086 Pitch Geometry Part 2, Front-Wheel Drive Lift. Regardless of the suspension type, when a vehicle accelerates with acceleration AX, the force acting on the front springs can be expressed by equation 21, and the ground reaction force can be expressed by equation 22. However, depending on the suspension type, the forces and moments acting on the pitch geometry differ. As explained in the previous video, in a solid axle suspension, the driving torque is transmitted through an internal shaft connecting the differential to the wheels, and the differential is not mounted on the sprung mass but is connected to the suspension links. Therefore, in the suspension geometry of a solid axle, since the differential is not mounted on the sprung mass, the engine torque does not generate a moment on the sprung mass. However, in an independent suspension, where the front-wheel drive differential is mounted on the sprung mass, an engine torque of magnitude Fxf multiplied by the wheel effective radius r is generated counterclockwise at the mounting point of the differential on the sprung mass, and a clockwise moment of magnitude Fxf driven by the driving force at the height of the virtual reaction point Sf is also transmitted to the sprung mass through the front suspension links. As shown in the figure, the directions of action of these 2 moments are exactly opposite. Consequently, in a solid axle suspension, only 1 moment is generated on the sprung mass with respect to the virtual reaction point Sf, whereas in an independent front-wheel drive suspension, the engine torque generates a moment at the differential mounting point, and the driving force, Fxf, acting on the tire contact point with the road surface, generates another moment with respect to the virtual reaction point, Sf. To clearly understand the difference in moments, between solid axles and independent suspensions, let's analyze in detail the moment generated in the sprung mass as the driving force produced by engine torque at the tire contact point. To analyze the differences between solid axle suspension and independent suspension, we will first examine the moment, MSF, generated at the virtual reaction point, SF, of a solid axle front-wheel drive vehicle. All physical quantities presented here have been explained in the previous video, E0086, Pitch Geometry Part 2, Front-Wheel Drive Lift. Let us review the vertical load. FZF is the road surface reaction force for the total vertical load of the vehicle acting on the front wheels. FZF is the sum of the reaction force for the static vertical load WSF and the dynamic vertical load generated by acceleration AX, and can be expressed as equation 22. Meanwhile, the force acting on the front spring can be expressed as equation 21 using the static vertical load WSF and the dynamic vertical load acting on the spring, delta WF. As a reaction to the driving force FXF generated at the center of the front tire contact surface, an upper arm reaction force F1 and a lower arm reaction force F2 are generated. The vertical resultant of these two forces is delta FZF, which acts vertically upward. In addition, since the driving force FXF acts parallel to the ground at a distance e, perpendicularly downward from the virtual reaction point SF, a moment of magnitude equal to the driving force FXF multiplied by the distance e is generated at the virtual reaction point SF. This moment is generated clockwise at the virtual reaction point SF. The moment MSF shown here is the total sum of all moments generated by all the acting and reaction forces explained so far. Since the positive y-axis direction is the direction coming out of the screen, the direction of the total sum of moments MSF shown in the figure is positive in the counterclockwise direction. As explained in the previous video, the sum of the moments generated by all these forces at the virtual reaction point SF must be 0, and if we define the counterclockwise direction as the positive direction, it can be expressed as equation 23. As shown in the figure here, the total driving force FXF acting horizontally to the road surface is transmitted to the sprung mass through the upper and lower links, and the sum of the vertical components of the upper and lower links transmitted perpendicularly to the sprung mass is delta FZF. Therefore, the ground reaction force is minus delta FZF. When acceleration AX acts on the vehicle, the magnitude of the total vertical dynamic load is transmitted through the links and springs, so this can be expressed by equation 24. From equation 24, since the force delta FZF is the resultant force of the link supporting the sprung weight, it can be seen that if the absolute value of the road surface reaction force, minus delta FZF, increases, the absolute value of minus delta WF decreases, and the force tensioning the spring decreases. This time, let us examine the moment, MSF, generated about the virtual reaction point, SF, in a front-wheel drive vehicle with independent suspension. FZF is the total vertical load of the vehicle acting on the front wheels. FZF can be expressed as equation 22, which represents the sum of the static vertical load, WSF, and the vertical dynamic load, generated by acceleration, AX. Meanwhile, the force acting on the front spring can be expressed as equation 21, using the static vertical load, WSF, and the vertical dynamic load, delta WF, acting on the spring. As a reaction to the driving force, FXF, generated at the front tire road contact center, an upper arm reaction force F1 and a lower arm reaction force F2 are generated, and the vertical resultant of these two forces is delta FZF. Furthermore, since the driving force, FXF, acts parallel to the ground at a location vertically downward at a distance e from the virtual reaction point, SF, a moment of magnitude equal to the driving force, FXF, multiplied by the distance e is generated about the virtual reaction point, SF. This moment occurs clockwise with respect to the virtual reaction point SF. Up to this point, it is the same as the solid axle suspension described earlier. However, in a front-wheel drive vehicle with independent suspension, since the differential is mounted on the sprung mass, the engine torque acting around the wheel center is generated on the sprung mass, and its magnitude can be expressed as equation 25. As shown in equation 25, this magnitude is equal to the value obtained by multiplying the driving force, Fxf, by the effective radius r of the wheel. This driving torque generates the front-wheel driving force, Fxf, and creates a moment with respect to the virtual reaction point, SF. Therefore, by adding the moment generated by the differential mounted on the sprung mass to the moment equation 23 for the solid axle suspension obtained earlier, the moment equation for the independent suspension can be obtained as equation 26. Since the sum of the moments generated by all forces about the virtual reaction point, SF, should be zero, and the counterclockwise direction is defined as the positive direction, all moments about the virtual reaction point, SF, can be expressed as equation 26. As shown in the figure here, the moment generated by the driving force, Fxf, acting horizontally with respect to the road surface at the virtual reaction point, SF, is equal to the driving force, Fxf, multiplied by E minus r, and it can be seen that, compared to a solid axle suspension, it is reduced by the driving force, Fxf, multiplied by the effective radius, r, of the wheel. Let's calculate the vertical spring displacement relative to the front wheel center for a front-wheel drive vehicle with independent suspension. To do this, it is necessary to determine the relationship between the previously mentioned front-wheel drive force, Fxf, the dynamic force, and the vertical dynamic force acting on the front spring, delta Wf. By rearranging equation 26, which calculated the moment with respect to the virtual reaction point, SF, in terms of the force acting on the spring, delta Wf, we obtain equation 27. Meanwhile, the vertical dynamic load acting on the spring, delta Wf, can be expressed as equation 28, using the front wheel rate Kf and the front spring vertical displacement relative to the front wheel center, delta F. In equation 28, Kf represents the front wheel rate and delta F represents the spring vertical displacement relative to the front wheel center. In the middle term of equation 28, the first term represents the vertical dynamic load of the entire vehicle when the acceleration is ax, and the second term represents the vertical component of the force acting on the suspension link, which is the link force. Kf delta F represents the vertical dynamic load transmitted through the front springs out of the total vertical dynamic load transmitted vertically to the front wheel center. Since no driving force acts on the rear wheels, the second term of equation 28 represents the link force of the entire vehicle. From equation 27, it can be seen that the vertical dynamic load transferred to the spring, delta Wf, is the difference between the first term on the right-hand side of equation 27, the total vertical dynamic load transferred to the vehicle, and the second term on the right-hand side of equation 27, the link force. In the case of solid axle suspension, the link force was the value of Fxf multiplied by E over d, but in the case of independent suspension, it changed to the value of Fxf multiplied by E minus r over d. Therefore, it can be seen that, when the virtual reaction point is at the same location, the link force of the independent suspension is smaller than that of the solid axle suspension. Thus, when the vehicle accelerates, if the virtual reaction point location is the same, the force transmitted through the independent suspension link is smaller compared to the solid axle suspension link, so the independent suspension spring transmits relatively more vertical dynamic load than the solid axle spring. Next, let's determine the condition for zero lift in a front-wheel drive vehicle with independent suspension. In a front-wheel drive vehicle, if no dynamic load acts on the front suspension springs, when the driving force is applied, the lift becomes zero. To prevent dynamic loads from acting on the springs, the front suspension link geometry must be configured so that the vertical force acting on the front link supports the total vertical dynamic load generated by the acceleration AX, thereby making the vertical dynamic load acting on the springs zero. Meanwhile, from the spring displacement of the front and rear wheels, we can determine the condition for making the pitch angle zero when the driving force is generated in a front-wheel drive vehicle with independent suspension. The front spring displacement was calculated using equation 28, and the vertical spring displacement relative to the rear wheel center can also be calculated from equation 29, using the previously calculated the vertical rear spring dynamic load, delta WR. In equation 29, Kr represents the rear wheel rate, and delta R represents the vertical spring displacement relative to the rear wheel center. First, let us examine the conditions under which lift becomes zero in a front-wheel drive vehicle with independent suspension. From equation 28, we can derive the geometric conditions of the suspension, where lift becomes zero. For lift to be zero, the force acting on the front springs must be zero, so equation 30 must be satisfied. Therefore, from equation 28, we can derive equation 31. Meanwhile, since the driving force Fxf can be expressed by equation 33, substituting Fxf from equation 33 into equation 31 and rearranging yields equation 32. For equation 32 to hold, the expression inside the parentheses must be zero, so we obtain equation 34, which represents the conditions for lift to become zero. Please remember that, for a solid axle suspension, the fraction on the right side of equation 34 was E/d for the zero lift condition, but for an independent suspension, it changed to E-r/d. Let's examine what geometry is required to achieve zero lift in a front-wheel drive vehicle with independent suspension. Based on the condition represented by equation 34 derived earlier, the geometry required to achieve zero lift can be represented as shown in the figure here. Point G contains the center of gravity, CG, and is the point where a horizontal line parallel to the ground intersects the vertical line, passing through the rear tire contact point B. Pitch geometry is analyzed based on the bicycle model. The forces acting on the left and right wheels combine into a single force at the vehicle's central longitudinal section. It is assumed that the vehicle's center of gravity is located at the vehicle's central longitudinal section. The black inclined line is the straight line connecting the front tire contact point A and point G. By translating this line in the positive z-axis direction by the wheel's effective radius r, we can obtain the blue line connecting points J and K. If the virtual reaction point, SF, exists on the inclined blue line between points J and K, then according to the property of triangle similarity, the ratio of H to L always has the same value as the ratio of E minus R to D, thus satisfying equation 34. Therefore, if the virtual reaction point, SF, of the front suspension exists anywhere on the blue line shown here, the vehicle does not experience lift during acceleration. In the figure, the blue line connecting points J and K represents the zero lift line of a front-wheel drive vehicle with independent suspension. From the above analysis, it can be seen that, in order to make the lift zero, the virtual reaction point of a front-wheel drive vehicle with independent suspension must be located further upward by the effective radius r of the wheel compared to the virtual reaction point of a front-wheel drive vehicle with a solid axle suspension. The fact that lift does not occur during acceleration does not mean that the pitch angle is zero. Let us examine the relationship between lift and pitch angle. Let's examine the relationship between zero lift and pitch angle when the driving force is applied in a front-wheel drive vehicle with independent suspension and the lift becomes zero. For the sake of convenience, we will assume that the front suspension wheel rate and the rear suspension wheel rate are the same. Cases where these wheel rates differ will be explained later by deriving the corresponding formulas. Zero lift means that the front spring displacement is zero, which implies that the front ride height has not changed. However, as indicated by the orange line in the figure, even though the front spring displacement is zero, the rear spring displacement is not zero, and the rear ride height has decreased. To make the pitch angle zero, the front ride height must be reduced to the rear level, lowering it to the level indicated by the grey line. To reduce the front ride height to the rear level, the virtual reaction point, SF, must be raised. Raising the virtual reaction point, SF, reduces the ground reaction force attributable to link forces, causing the front suspension links to support less vertical dynamic load. Consequently, the vertical dynamic load that the front springs must support increases. If the height E of the virtual reaction point, SF, lies on the straight line, connecting points J and K, no force acts on the spring, and all load transfer occurs through the links. In the case of front-wheel drive, if the height E of the virtual reaction point, SF, lies above the straight line, connecting points J and K, the force compressing the spring during acceleration becomes greater than the force compressing the spring in the steady state, so the front ride height actually decreases. As the force acting on the spring increases, the load transfer through the front suspension links increases in a direction that reduces the ground reaction force. By utilizing this fact, one can find the location of the front suspension's virtual reaction point that reduces the front ride height so that the pitch angle becomes zero. Keeping this in mind, let's examine the pitch angle. Let's calculate the pitch angle when a front-wheel drive vehicle with independent suspension accelerates. By determining the spring displacement of the front and rear wheels, we can calculate the pitch angle when driving force is generated in a front-wheel drive vehicle with independent suspension. Regarding the front suspension, the front spring displacement was calculated using equation 28. Regarding the rear suspension, the rear spring displacement could also be calculated from equation 29, using the previously calculated vertical dynamic load in rear spring, delta WR. In equation 29, KR represents the rear wheel rate, and delta R represents the vertical spring displacement, measured along a vertical line, passing through the rear wheel center. Meanwhile, since the front-wheel driving force FXF is equal to the vehicle mass, multiplied by the acceleration AX, it can be expressed as in equation 35. When the pitch angle phi is small, an approximation can be used, where the tangent phi p is equal to phi p. In this case, phi p is in radians. After rearranging equation 28 for the front spring displacement delta F, and equation 29 for the rear spring displacement delta R, substituting these two displacement values into the second equation of equation 36 yields the pitch angle phi p when a driving force is applied in a front-wheel drive vehicle with independent suspension, as shown in the third equation of equation 36. By substituting Fxf from equation 35 into the third equation of equation 36 and rearranging it, the pitch angle phi p can be expressed as equation 37. The pitch angle phi p expressed by equation 37 indicates that, as expected, it can be expressed as a function of acceleration, mass, front and rear wheel rates, and the geometry of the suspension links. Equation 37 is identical to the pitch angle equation for a front-wheel drive vehicle with solid axle suspension, except that E is changed to E minus R. Let us continue to determine the condition under which the pitch angle becomes zero when a front-wheel drive vehicle with independent suspension accelerates. In equation 37, which represents the pitch angle phi p derived earlier, if the driving force is applied and the acceleration ax is not zero, the condition for the pitch angle phi p to become zero is that the sum of the terms inside the parentheses in equation 37 becomes zero. Therefore, deriving the condition for a zero pitch angle from equation 37, it can be expressed as equation 38. Simplifying equation 38 for E minus a divided by d yields equation 39. The first term on the right side of equation 39 represents the anti-lift condition of equation 34, which was derived earlier. As explained previously, in general suspension geometry, the condition for zero lift is not the same as the condition for zero pitch angle. The second term on the right side of equation 39 explains that if the difference between the front suspension wheel rate and the rear suspension wheel rate is not significant for the pitch angle to become zero, the height of the center of gravity must either drop by nearly half under the condition of zero lift, or the value of E00 minus a must increase by nearly double. From equation 39, if the rear wheel rate has a significantly larger value compared to the front wheel rate, the second term of equation 39 can be ignored, so it can be seen that the conditions for zero lift and zero pitch angle are identical. If the front suspension wheel rate and the rear suspension wheel rate are equal in equation 39, the condition for zero pitch angle can be expressed as equation 40. Let's verify the above explanation with a figure. Let's examine what geometry is required to make the pitch angle zero in the case of a front-wheel drive vehicle with independent suspension. Based on the conditions expressed by equation 39 derived earlier, the geometry required to make the pitch angle zero can be represented as shown in the figure here. To make the explanation efficient, I will use equation 40, which assumes that the front wheel rate kf and the rear wheel rate kr are equal. In the figure, point S contains point U, which is at twice the height of the center of gravity, cg, and is the point where a horizontal line parallel to the ground intersects the vertical line, passing through the rear tire contact center B. Additionally, the line connecting points J and T is the line connecting points A and S, translated by a distance r in the positive z-axis direction. To satisfy equation 40, the ratio of the height of twice the center of gravity to the wheelbase must be equal to the ratio of E minus r to d. The line satisfying this condition can be represented by the green dotted line in the figure. The green dotted line is a straight line connecting the front wheel center J and point T. Since triangle ABS and triangle JIT are identical triangles, triangle ABS and triangle JCO are similar. Therefore, the ratio of E minus r to d is equal to the ratio of twice the height of the center of gravity to the wheelbase edge. Expressing this result as an equation, we get equation 40. Consequently, if the virtual reaction point SF of the front suspension exists anywhere along the green dotted line shown here, a front-wheel drive vehicle with independent suspension can maintain a zero pitch angle during acceleration. As explained earlier, when driving force is applied in front-wheel drive vehicle, in order to maintain the pitch angle attitude, the front ride height must decrease by the same amount as the rear ride height decreases. Therefore, the final vehicle attitude with zero pitch angle inevitably results in both the front and rear ride heights decreasing, and the vehicle attitude is ultimately the one indicated by the gray line. Is it possible for the front ride height of a vehicle in acceleration to be lower than rear one? If the front ride height decreases, why is that? Depending on the location of the virtual reaction point, the front ride height of an accelerating vehicle can either rise or fall. However, the general suspension geometry of commercially available vehicles is designed so that the front of the vehicle rises during acceleration. I will explain why it is designed this way in a subsequent video. By describing the 7 cases shown in the figure, I will explain that the front of the vehicle can either rise or fall during acceleration. In the figure, the blue arrows represent the forces acting on the springs, and the red arrows represent the forces acting on the links. First, the vertical dynamic load, derived from Newton's second law, is represented by the second term of equation 22. Since this value is determined by the laws of physics, it remains unchanged once the acceleration is constant, regardless of the vehicle's suspension geometry. In the typical suspension geometry of commercially available vehicles, the front virtual reaction point SF lies in the region between the horizontal line, connecting the front wheel center, point J, and the rear wheel center, point I, and the lift zero line, connecting points J and K. This region is shown in light green in the figure. In this case, as shown in figure 3, both the forces on the suspension links and the vertical dynamic load acting on the springs act vertically upward. These forces are tension forces on the springs and links. Here, eta represents the ratio of the force acting on the suspension links to the total vertical dynamic load. In the case of figure 3, the eta value is greater than 0 and less than 1. Figure 4 illustrates the case where the virtual reaction point lies on the lift zero line, connecting points J and K. In this case, since the lift is 0, the vertical dynamic load acting on the springs becomes 0, and the vertical dynamic load acts solely through the suspension links. This force is tension force on the links. In this case, the eta value is 1. Figure 6 illustrates the case where the virtual reaction point SF lies on the pitch angle 0 line, connecting points J and T, in which case the pitch angle is 0. In this case, the vertical dynamic load acting on the spring acts vertically downward as a compressive force, and the vertical dynamic load acting on the link acts as a tension force, which is twice the total vertical dynamic load transmitted by the vehicle. At this time, the value of eta is 2. Let's continue to examine the locations of the remaining virtual reaction points. Figure 1 illustrates the case where the virtual reaction point lies in the area below the horizontal line, connecting the front wheel center, point J, and the rear wheel center, point I, and is shown in light yellow. In this case, based on absolute values, the vertical force tensioning the spring is greater than the vertical resultant force compressing the links. In this case, the eta is negative, less than 0. Figure 2 illustrates the case where the virtual reaction point lies on the horizontal line, connecting the front wheel center, point J, and the rear wheel center, point I. In this case, the vertical resultant force of the links is 0, and only the vertical force tensioning the spring exists. In this case, the eta is 0. Figure 5 illustrates the case where the virtual reaction point lies between the lift zero line, JK, and the pitch angle 0 line, JT, and is shown in light red. In this case, the force tensioning the links acts vertically upward, and the force compressing the spring acts vertically downward. Based on absolute values, the forces of the links are greater than the spring forces. In this case, the eta value is greater than 1 and less than 2. If a virtual reaction point exists in this region, the front ride height decreases. However, the front ride height is still higher than the rear ride height, so the vehicle stance is high at the front and low at the rear. Figure 7 illustrates the case where the virtual reaction point, SF, is located in the region above the line, connecting points J and T. Since the front ride height decreases, compared to the rear ride height, the vehicle stance is low at the front and high at the rear. A force greater than the dynamic load transfer compresses the springs, and a force more than twice the dynamic load transfer, tensioning the links. In this case, the eta is greater than 2. Let us analyze all the points explained above at once. The figure here simultaneously shows the vertical force of the spring and the resultant vertical force of the links acting in the regions of the 7 virtual reaction points explained earlier. As explained, when a vehicle accelerates with constant acceleration ax, the vertical load transfer of a front-wheel drive vehicle, derived from Newton's second law, is given by equation C and has a constant value that does not vary depending on the suspension and drive type. Therefore, when the vertical force acting on the spring and the resultant vertical force of the links are added together, the value expressed by equation C must be the same in any case. Equation C represents the resultant force acting vertically upward on the spring and links, not the ground reaction force. By using eta, the ratio of the resultant vertical force of the links to the total load transfer, the vertical force of the spring and the resultant vertical force of the links for the 7 virtual reaction points can be easily analyzed. Number 1 indicates that, if the virtual reaction point lies below the horizontal line of the wheel center, the eta is negative, and the force tensioning the spring is greater than the force compressing the link. Number 2 indicates that, if the virtual reaction point lies on the horizontal line of the wheel center, the eta is 0, and only the force tensioning the spring acts, while the force compressing the link is 0. Number 3 indicates that, if the virtual reaction point lies between the horizontal line of the wheel center and the lift 0 line, the eta is greater than 0 and less than 1, and both the vertical force tensioning the spring and the vertical resultant force tensing the links are vertically upward. Number 4 indicates that, if the virtual reaction point lies on the lift 0 line, the eta is 1, the vertical force tensioning the spring is eliminated, and only the vertical resultant force tensing the links acts. In this case, the lift becomes 0. Number 5 indicates that, if the virtual reaction point lies between the lift 0 line and the pitch angle 0 line, the eta is greater than 1 and less than 2, meaning the vertical force compressing the spring acts downward, and the vertical resultant force tensioning the links acts vertically upward. Number 6 indicates that, if the virtual reaction point lies on the pitch angle 0 line, the eta is 2, meaning that, based on absolute values, the vertical resultant force tensioning the links acts vertically upward and is twice as large as the vertical force compressing the spring acting vertically downward. In this case, the pitch angle becomes 0. Number 7 indicates that, if the virtual reaction point lies in the region above the pitch angle 0 line, the eta is greater than 2, meaning that, based on absolute values, the vertical resultant force tensioning the links acts vertically upward and is more than twice as large as the vertical force compressing the spring acting vertically downward. In this region, the front ride height is smaller than the rear ride height. Let's find the answer to the quiz. Which of the following correctly describes the relationship between the position of the front virtual reaction point and the ride height in a front-wheel drive independent suspension vehicle? 1. The position of the virtual reaction point and the ride height are directly related. 2. As the position of the virtual reaction point increases, the front ride height decreases. 3. The position of the front virtual reaction point and the rear ride height are unrelated. 4. As the position of the virtual reaction point increases, the front ride height decreases. 5. The position of the virtual reaction point and the rear ride height are unrelated. Number 4 is the correct answer. Let me summarize the content of this video. In front-wheel drive vehicles, we explained the pitch motion characteristics of solid axles and independent suspensions. The characteristics of a solid axle suspension are as follows. Driving torque is transmitted to the wheels through an internal shaft connecting the differential to the wheels. The differential is not mounted on the sprung mass but is connected to the suspension links. Engine torque does not generate a moment on the sprung mass. The zero lift line passed through the center of the front tire contact with the road surface. The characteristics of an independent suspension are as follows. Engine torque is generated at the differential mounting point on the sprung mass. The differential is mounted on the sprung mass. Engine torque generates a moment on the sprung mass. Engine torque must be included in the moment equilibrium equation. The zero lift line passed through the front wheel center. 7 pitch geometries during acceleration of a front-wheel drive vehicle equipped with independent suspension have been described. When the virtual reaction point is below the horizontal line connecting the wheel centers of the front and rear wheels, the increase in front ride height is greater than the decrease in rear ride height. When the virtual reaction point is on the horizontal line connecting the wheel centers of the front and rear wheels, the increase in front ride height is equal to the decrease in rear ride height. When the virtual reaction point is between the horizontal line connecting the wheel centers of the front and rear wheels and the lift zero line, the increase in front ride height is smaller than the decrease in rear ride height. When the virtual reaction point is on the lift zero line, the front ride height remains unchanged while the rear ride height decreases. When the virtual reaction point is between the lift zero line and the pitch angle zero line, the decrease in front ride height is smaller than the decrease in rear ride height. When the virtual reaction point is on the pitch angle zero line, the decreases in front ride height and rear ride height are equal, and the pitch angle is zero. When the virtual reaction point is above the pitch angle zero line, the decreases in front ride height becomes lower than the decreases in rear ride height. Therefore, in this case, when the vehicle accelerates, the front becomes lower than the rear. If you watch the previous videos, you can learn about various fields of vehicle dynamics and enjoy a more in-depth understanding of future videos. In my recent video, E0084, Pitch Geometry Part 4, I explained how to analyze pitch geometry using the front wheel braking force distribution coefficient when braking a vehicle. Additionally, we explained how to make dive and rise zero, and how to make the pitch angle zero using pitch geometry. In a recent video, E0085, Pitch Geometry Part 5, I explained the suspension geometry that makes the squat zero and the suspension geometry that makes the pitch angle zero when accelerating an independent rear-wheel drive vehicle, and explained the vehicle attitude according to the pitch angle determined by 7 positions of the virtual reaction point. The next video will be Pitch Geometry Part 6. I will explain how to analyze rise in the pitch motion for the outboard rear brakes. If you found this video helpful, please hit the thumbs up and catch the brand new videos by free subscription. Also turn on alarms to be the first to see new videos. So, what are you waiting for? See you at next videos. Goodbye, guys.